Hello, welcome to another talk from a desk of Ross Finlayson here in Seattle, Washington, the end of the year, so in 2023. What I thought today is that I would start a new sort of dialogue about moments and motion. And this has basically two aspects. One is that in our technical models, that motion is waves. That a motion is considered as the carriage of an event in a series and a sequence of events in time, where everything is so parameterized by time, and that in our model of particle wave duality and the from the quantum scale to then the classical and the mesoscale, the Galilean, and then as up to the very large, the cosmological scale, that moments and motions reflect this notion of state, a moment, and motion here is waves in this first aspect. Then the second sort of aspect is geometry as motion. That geometry itself is state, as a moment, but that geometry and motion become the same thing. The geometry is motion. So as sort of the realm of thought of these things is that besides living in time, being in the course, in the river in the flow of time, then we think about it and we have mental models and make reasonings as with regards to the temporal, the contingent, past and future events as it may so be, with regards to, what's history is history and what's in the future will be, with regards to how according to intelligence and being actors that it can be made to be, or what will be, que sera, vis-a-vis determinism, chance and uncertainty, and will and actions of will. So regards the picture of passage in time as of altogether a unified sort of concept. So what I thought to do was, and this is in the context of the philosophical foreground, that it reflects the technical philosophical foreground. And so questions of time and the infinite divisibility of time, or motion, and the notions of relative motion and constant motion, and rest, have a very strong concept arising from the Eleatics of pre-Socratic Greece in the ancient times, or kind of what was the first kind of formalized canon that we still have as a tradition to carry on, vis-a-vis the times before that, where the same sorts of notions and concepts would have as arisen from the Occident or the East, or India, the Vedas, and these kinds of things before the history is available, and the pre-Diluvian, for the antediluvian, with regards to events in history, and with regards to 2500 BC, and the time of the Eleatics. So Zeno of Elea has these thought experiments with regards to motion and meeting and parting, and starting and stopping, and motion and rest. And so he's got the stories of Achilles and the tortoise, and they engage in a foot race, and as to how the tortoise, with any sort of advantage at all, would, according to a regression via induction, that induction sort of fails at some points when the inductive impasse is reached and not surpassed. That Achilles, according to these thought experiments, by an argument that is simple and declarative and inductive, would, though he has a faster velocity than the tortoise, where the tortoise as an animal is known for its shell, and it's known for its slowness, whereas Achilles is a model runner of arbitrarily high velocity with regards to the tortoise. So that's one of the framings of Zeno of Elea's arguments about moments in motion with regards to at a moment and the instantaneous rate of change, instant being the instant of a moment, that it's with regards to it's just an individuum of a time in the time, the passage of time, the forward carriage of time. So moments in motion help reflect a lot of these concepts that get into why things can be so. And today we would just frame that as related rates problems. You got rate A, rate B, how do they relate? It's so possible to find them proportionately, and with regards to the computations of displacement over time, that it's pretty simple to arrive at a reasonably good theory where the primitives of motion and rest for itself and starting and stopping for itself are already given, that then everything else follows very, of course, perfectly from that. Related rates. And with regards to then via a diagram or a chart, or the fact that their events coincide where they part and meet. So that's one idea of Zeno's thought experiments, which everyone should be familiar with and explore, so that they kind of understand that in terms of the reasoning, that there is the grounds for deductive reasoning to apply and to help explain why otherwise the traditional or classical logic has its limits. And it's funny, later we call that, we surpass that being, we've defined a limit that it reaches, it attains to, and it reaches it somehow. The other notion of a Zeno of Elea then is the archer, and so the archer kind of represents the first sort of geometric series in numbers that add up an infinitude of them to finite value. So you have half the distance from the archer to his target, and half of that, and half of that, and half of that, again, infinitely divided, infinitely divisible, results that the sum of the series of the inverse powers of 2 is equal to 1. And then today, after Cauchy and Weierstrass, we can say that the limit exists and equals 1. Then that the limit exists and it's also the sum has, with regards to trying to avoid further complications with the vagaries of the impredicativity or quantifier ambiguity, or otherwise with regards to why induction fails and deductive analysis then establishes a wider frame, a larger frame in the dialectic to solve these kinds of things. That Zeno's arguments are considered the classical exposition of continuous motion and continuous time. And there's that in all of the history of the developments of these sorts of arguments, is that it's so simplified according to that it reflects a unit distance and a unit time and the relation in rate to distance, or between the various notions that we have, and it's still exactly so all throughout the theory, the time-like and the space-like. And then that we have 3 space dimensions. There's a ray of time that we can project and perceive as of another dimension of time. And then with regards to the light-like, that then according to that we have the L principle for light, that's given the running as about the constants as to why modern theories like after Kaluza-Klein and most theories of physics put together have that as like so, that there's the space-like, the time-like, and the light-like. So for moments and motion, the idea is, what I figured to study was a little bit, because I'm not really the greatest analyst when it comes to wave mechanics, has that the wave mechanics is our primary model of things that both or either are of periodic motion that oscillate as their recitative and reconstitutive periodic motion, and traveling motion, or linear motion as it's generally arrived at. So, and then with regards to rotational, with regards to the linear, with regards to the kinematics, as are what are connected kinetics, that the wave model is the usual thing. And so what's usually explored in the courses is, after having studied trigonometry and the sinusoidal and the notions of periodic functions, the periodic functions then are so parameterized by time reflect periodic motion. And so there's a couple different cases that everyone had to sit through and see as derivations and later apply, that included the motion of the pendulum, and that's because gravity affords is like there's basically an infinitely deep well of potential. The pendulum swinging back and forth is ideal in a sense, and the spring. So with regards to the spring, is kind of like the spring is fixed at one or the other side. So with regards to wave motion, it's like there's not an infinitely deep well of potential under which it is. So then those get into the notions that we have usually the periodic functions have a period of 2 pi or sometimes 2a, and then with regards to why that is so is because pi is pi radians, and so 2 pi radians is the circumference of a circle, and it's traced out each one of these rotations, each one of the periods, as of by this transcendental constant, which is well known, and this is the ratio of the circumference to the diameter of a circle, pi, 3.1415926, ... And then the other idea is to assign it to a particular fixed constant, A, is that we kind of divide it out that way, and it results that then when we're dealing with signals that are like, I'm just dealing with signals that are from 0 to 1 and 0 to 1 and 0 to 1 repeating indefinitely, it just kind of reduces this to a constant as well. So that's why it's seen like pi over a is a regular kind of ratio in these constants, because we have the model of periodic motion and the spring, the pendulum, and then that's as with regards to the circuitous of around the circle, and then we have the back and forth plainly and oscillating, which is with regards to on off, and these kinds of things. So these are the usual kinds of derivations that everybody had to sit in mechanics. So in physics, you start with the mechanics, which is classical, and with regards to Newton's laws, and what is in motion stays in motion, what is at rest stays at rest, and then when two objects in motion collide, then they have equal and opposite reactions. You notice he doesn't really say what's the moment when it changes or anything like that. It's not defined. It's modeled as ideally by perfect inelastic collisions of things that do move, that happen to interact. Then with regards to gravity and things that interact, not mechanically, kinetically, as by the rigidity of their collision, or interference and non-interference, is the overall field of gravity, or any kind of field that represents a field of vectors of force. So our theories have forces in them, and then the unified field theory is just kind of put them all together in a common lattice, vis-a-vis that the forces are attached to the moments, and then in fact they all live in the field. So our field theory is still a force theory, and this kind of thing. That then what we get into after mechanics and then the models of the pendulum and the spring as a representative of wave motion, is that then the theory of wave motion has applied various notions of these kind of waves. And so this is then where I'll start. I've selected some books from which I'll try to find some derivations and inspiration, And so one of these, I imagine, is this one called Waves. And what it is from this mathematical, university mathematical texts. see that this here is vector methods, and then this here is integration of ODEs. One of these fellows over here is a primer of real functions, waves. So we have Coulson's waves, and what it reflects is that it will have a stately, gentle, and a didactic approach to these sorts of things, as would usually be then used throughout all the following courses as fundamental. So what this is then is one of these books. And then some other things I got here, and I thought might be apropos, is here's this Discoveries and Opinions of Galileo. So the Galileo and the Galilean, basically he establishes invariance and all these kind of usual symbolic formulas for one of the parameters is time, and you can reflect things in terms of time and how they go. This being granted, Galileo says, I think that in discussions of physical problems we ought to begin not from the authority of scriptural passages, but from sense experiences and necessary demonstrations. For the Holy Bible and the phenomena of nature proceed alike from the divine word, the former as the dictate of the Holy Ghost, and latter as the observant executrix of God's commands. So this is from a time and place where it is dogma that the entire notion of determinism was as deistic. And so Galileo suffered a bit of persecution for sticking his neck out to help explain, to modernize into a theory where science is so. Where then, as we still have this teleological connection to the ontological, that's ultimately teleological, the first cause and final principles of things. Vis-a-vis the ontological, which is that we have a declarative and a didactic theory of science and the scientific method. And it's after the empirical, and then now we have it as for the theoretical, and it still comes up as from that for a teleological, which explains things, teleological, which explains things, and the ontological, which is bodies of collected knowledges according to definitions and derivations. So, looking into then further his readings, a lot of this is his efforts to convince the other scholars in his realm why it should be explored and the exoteric this way. And there's much politesse, and then he talks about Ptolemy. So we have the Copernican revolution after the Ptolemaic revolution, and then we have the kind of the Keplerian revolution and the evolution, and then Newton. We got Kepler with the system of the world and Newton with the system of the world. And so those then arrived at from the geocentric to the heliocentric, and then with regards to even beyond that the origin is everywhere, and these kinds of things. That in with regards to moments in motion, there are moments in time series data, when the motion of these events, the concepts arose, vis-a-vis the moments as about the orbits of things, that the entire other concept of Newton's laws are about the orbits, according to the fields and the forces they lay in, and this kind of stuff. That then the thread, the silver thread, or what connects us to that history and its apologetics and this development of theory, and including as well that these theories have ideals, and when we learn new ones, we still keep the old ones with respect to the celestial spheres and these kinds of things, the cosmological notions of things vis-a-vis the substance elements of things, which for the Greeks were like the four ancient elements: earth, air, fire, water. Fire is change, and this kind of thing, vis-a-vis that as a theory develops, and from this teleological and the ontological, and then the ontological commitment or attachment to things, has that over time, Galileo is held up as a very important school of a man who is related to these disclosings, the revealings of these concepts, with the idea that in a Platonic universe that mathematical truths are discovered, not invented. Well, at the same time, for some overall teleological entity that they are so. So Galileo is very important, and they have his experiments with regards to what became Newton's laws. Then that later and after that, Newton's adoption, invention, and discovery of various notions and motions of the integral calculus allowed him to then also use that with regards to an analysis of the Keplerian and why orbits after the geocentric and heliocentric came to have that. Then there was the immobile celestial spheres, that there as ellipses, which have their own tautochronous properties. That then Newton's system of the world and its prediction of the places of planets in the sky according to the telescope survey of the day was a big, huge deal. And Galileo had a telescope. The illustrious ambassador. Your Excellency and their Highnesses through you. You should know that I have received a letter, or rather an 8-page treatise from Johannes Kepler, the imperial mathematician, written in approbation of every detail contained in my book without the slightest doubt or contradictions of anything. During the Spanish Inquisition, it was a terrible time in Spain, and in the Roman Inquisition, Galileo was prevented from disclosing his discoveries till a later date. Descartes was put out as disclosed discoveries in that time, in that place. Galileo's day-by-day journal of observations continued in unbroken sequence until 10 days before publication of the book, which he remained in Venice to supervise. The observations omitted here contain nothing of a novel character. So, and this is just his astronomical observations, and the nebula Praesepe, the nebula of Orion. Praesepe lies in the constellation Cancer. So Galileo, and he uses geometry for things, diagrams, according to the pictorial. The ether, or ever-moving, was a special substance of which the sky and all the heavenly bodies were supposed to be made, a substance essentially different from all the earthly elements. In later years, Galileo abandoned his suggestion here that the moon has a vaporous atmosphere. So today we know that there's a notion of that nature abhors a vacuum, meaning that the natural propensity and tendency of things is to fill a vacuum, because it's just things would naturally fall into a space of this lesser configuration of active energy to such a thing. But at the same time, it's known that largely the observable universe is mostly empty. But we're all in it, you know. The whole firmament and foundation is in it. So with his telescope, he studied the moon. Pythagoras was a mathematician and philosopher of the 6th century BC, a semi-legendary figure whose followers were credited at Galileo's time with having anticipated the Copernican system. This tradition was based upon a misunderstanding. The Pythagoreans made the earth revolve about a central fire, whose light and heat were reflected to the earth by the sun. Now, one of these things about the received tradition and how it got deconstructed into simpler and simpler and simpler accounts and elements, which still kind of revolved around the same universals, their particulars, is that through the reading of the lens in the oculum, the idea is that then we still have to say, hey, if they did know what they were talking about, then that is still within the essence of these things. So it's pretty usual in that sense that we have a very rich and detailed science today. The year 1609. De Revolutionibus Orbium Celestium. So that's his great book. Unknown to Copernicus, a preface had been anonymously added to his book by an officious clergyman advising readers that the ideas in it were to be construed not literally, but merely as hypotheses useful in simplifying the work of astronomers. And you can read that in several ways, and one it was as of exactly that, and another is that is like actually our esoteric and internal science already kind of includes things that kind of preclude it. So this is already set up in a different kind of way, and it's kind of down in the study, but this kind of stuff. If modern physicists care nothing for the works of Galileo, that is a matter of taste and not merely one of progress. Modern poets still read Homer, modern philosophers Plato. Not only because those works are excellently written, but also because they throw light upon the origins of poetry and philosophy. So Galileo is great and important, and his theories, as what come out after it, is after Kepler, are adapted by Newton, but Kepler is really the big guy. So this isn't yet the wave theory book that I wanted to get into yet. We're going to get into some technical books on waves. Vis-a-vis this little tome right here, and this and that right here. So this then is just the epitome of Copernican astronomy by Johannes Kepler, and it's pretty great. The harmonies of the world, harmonices mundi, epitome astronomy Copernicae, the epitome of Copernican astronomy. The Hipparchus. This latter work utilized a portion of the material Kepler had been gathering for a project to comprehend the whole scheme of the heavens, to be called the Hipparchus. There's a recent part of the sky survey called Hipparchos. It's an experimental station in space launched from Earth, I believe. There are a couple different settings where the ground or terrestrial and the space-based kind of are all connected. Kepler. The Rudolphine tables, the compilation of his own and Brahe's astronomical tables. So Tycho Brahe and Johannes Kepler, or Joe, or whatever he's going by these days, Kepler. Epitome of Copernican astronomy. On the causes of the true irregularities, vis-a-vis on the principal parts of the world, on the place of the sun at the center of the world. How many and of what sort are the movements? So Kepler is of a time and place the greatest, or as what we have so received from that time and place. He frames things in terms of questions and answers. So he'll pose a brief question and then provide his opinion and the reasonings and justifications thereof. What answer does Aristotle make to this argument, which is the argument that on the place of the sun at the center of the world? By what arguments do we affirm that the sun is situated at the center of the world? The very ancient Pythagoreans and the Italian philosophers supply us with some of these arguments in Aristotle. These arguments are drawn from the dignity of the sun and that of the place, and from the sun's office of vivification and illumination of the world. State the first argument from dignity. This is the reasoning of the Pythagoreans according to Aristotle. The more worthy places do the most worthy and precious body. Now the sun, for which they use the word fire, as sects purposely hiding their teachings, is worthier than the earth and is the most worthy and precious body in the whole world, as was shown a little before. But the surface and center or midpoint are the two extremes of a sphere. Therefore, one of these places is due to the sun, but not the surface, for that which is the principal body in the whole world should watch over all the bodies, but the center is suited for this function, so they used to call it the watchtower of Jupiter. And so it is not proper that the earth should be in the middle, for this place belongs to the sun, while the earth is borne around the center of its yearly movement. So there's quite a bit that goes in this. It's kind of like on the multiplicity of worlds, conversations on the multiplicity of worlds. It's kind of immaterial. We have one here, and we already have one. So, waves. Elementary standpoint, as many different types of wave motion as possible. So wave motion is varied. There are traveling waves. There are stationary waves. There are there are names for all sorts of waves. There are waves in layers. There are waves in media. There are waves of objects. There are waves of about objects. There's any kind of notion of whatever reciprocates is as of a wave, and whatever is a Boolean or bubbles is as of a wave. So waves there's the front of the wave front, or when the wave is on the surface, the wave crest. So wave is either within a medium or the surface of a medium. Surface waves, bulk waves. So. A few topics, such as elastic waves in continuous media or at the common boundary of two media and radiation from aerials, have unavoidably had to be omitted for lack of space. The readers refer to any of the standard works on elasticity and wireless for a discussion of those problems. Then he thanks his friends Dr. Rutherford and Rushbrook, who have read the proofs, checked most of the examples, and contributed in no small way to the clarity of the arguments. So, as an introduction, I'd just like to see if there's anything particular that sticks out as that hasn't been mentioned. We're all familiar with the idea of a wave, surface waves and bulk waves, and then sometimes when you think of like an object swimming through a medium, that it doesn't necessarily make waves, but it has waves about itself. It's what radiates is in another sense what a wave is. So you can think of as a wave both as like the surface, which as it oscillates and is restitutive and reconstitutes itself, doesn't affect overall like an arbitrarily larger region outside, but at the same time it radiates that energy outward. The gravitational wave is kind of a high level concept. It's like what is beyond the sense of the electromagnetic and beyond the sense of the optical. What is the idea of a gravitational wave? And then can it really travel as fast as gravity travels? This gets into various theories where whether, according to the theory, that the normalized units of light speed are 1 or infinity. And then as with regards to when it's 1, then with regards to whether gravity's speed is infinity. In this solar system, it is well known that the force of gravity is, according to a force model in a field theory of the force of gravity, does not point at the image of another object, which is behind it, according to the time it takes light to travel that far. It points at the source of the image, which is as of instantaneous. And if a giant claw were to pluck the moon out of the sky and disappear with it, the ripple would be as of instantaneous. There's a laboratory called Batavia in Chicago. There's a giant lake in Baikal on the other side of the world. And in this lake, it's like a mile deep lake. It's one of the deepest freshwater lakes in the world. So they set up an array. It's about 1 kilometer cube of an array of sensors and detectors. So in Batavia, they have what's called a neutrino generator. And so they shoot them all the way through the Earth, straight through the Earth, from Batavia to Baikal. It's called a neutrinophone. It's real time. Thus the ripples spread outwards over a pond, carrying energy with them. But as we can see by watching the motion of a small floating body, the water of the pond itself does not move with the waves. This is, we have kind of like the notion of the front of the wave or the crests and troughs of the waves on the surface. They are all governed by a certain differential equation, the equation of wave motion. And the mathematical part of each separate problem merely consists in solving this equation with the right boundary conditions and then interpreting the solution appropriately. Consider a disturbance phi, which is propagated along the x-axis with velocity c. So the propagation equations are the big key thing. What propagates? How does it propagate? So this is addressed in these early readings from Maugin and Einstein and the path integral of Swanson about the propagation, and the propagation equations are key, and they define how fast does a front move, and it's a particle, how fast does a particle move. So there is no need to state explicitly what phi refers to. It may be the elevation of a water wave or the magnitude of a fluctuating electric field. So then, since the disturbance is moving, phi will depend on x and t. X displacement and t time. When t equals 0, phi will be some function of which we may call f of x. So he introduces at least that we're dealing with the world of functions, and so according to the parameters of functions and the values, then the functional relation holds up. Their functions are continuous functions. They affect and reflect it. Any arbitrarily small change will be reflected with an arbitrarily small change, and that they're related, connected together, as with regards to then discontinuities, singularities, these kinds of things. F of x is the wave profile. Since we plot the disturbance of phi against x and photograph the wave at t equals 0, the curve obtained will be phi equals x. So at the moment, instantaneously, it's kind of like so. If we suppose that the wave is propagated without change of shape, then a photograph taken at a later time t will be identical with that at t equals 0. Except that with the wave profile has moved a distance ct in the positive direction of the x-axis. So we'll often end up with very usual and familiar names for the variables, and because that way they're the same when they show up later on all sorts of the associated mechanics and the machinery of the functions and the functional systems, that what it'll be will have the same names, and so that are often employed throughout. Because otherwise it's to be made understood that you can just relabel things, and it's really that they are what they are by what they are, vis-a-vis they are what they are by what they're called. So if we suppose that the wave is propagated without change of shape, then a photograph taken at a later date t will be identical with that at t equals 0, except that the wave profile has moved a distance ct in the positive direction of the x-axis. So we took a new origin at the point x equals ct and let distances measured from this origin be called x, so that x equals big X plus ct, then the equation of the wave profile referred to this new origin would be phi equals f of big X. Refer to the original fixed origin, this means that phi equals f of x minus ct. And so this coefficient and its distance helps reflect essentially the periodic and repeating nature of a thing. And so there's some notions that things attenuate and dissipate over time, vis-a-vis that they oscillate as about being so and repeating. That oscillation and restitution and dissipation and attenuation are here two primary concepts which affect and reflect the notions of the tendencies and propensities of things to change or stay the same or revert to the same or vary. The simplest example of a wave of this kind is the harmonic wave, in which the wave profile is a sine or cosine curve. So we talked a little bit about the sine and cosine, the sinusoidal, about how they have their usual notions about the Pythagorean theorem and going around the circle, and with regards to particular properties of being orthogonal functions, so that when you integrate them taken together as a product, it equals 0, or as with regards to where it equals 1 when they're in and out of phase. That when two sine curves are in phase, that's when they coincide, and when they're out of phase, they coincide. And it just so happens that a cosine curve that's completely out of phase with itself is the same as a sine curve. Then there's also that for the trigonometry, then there's the trilateralometry, that if you take, instead of a right triangle and trace it as around a circle, you take an equilateral triangle and you unhinge it and roll it open and then flip it over and roll that open and flip it over and roll that back. Draws the same curve. And like a spirograph, in a sense, that would work the same for higher order polygons, which is not really the same thing as for there's not really another triangle to draw in the circle to draw the chords of the radii as about it. So the trilateralometry opens up a whole wider thing called trigonometry, and these are people don't really explore this because it's hard enough just to learn that you have to learn trigonometry and be familiar with its identities, because all throughout these later courses, these exact same things are going to be used to build up all the rest of it. It's called the linear curriculum. Everybody's had to sit it to graduate and get a degree in a scientific or technical field where they're expected to be able to reason about these things, besides conceptually, which is important, and having a sense of things, but so that they're not adrift and unable to make things fungible and keep things fungible with regards to the familiarity of the dexterity of the manipulation of formulaic identities and formulaic representations of things. Quantified. So, of course, this is very resistant to change because it's been the curriculum forever. The harmonic wave, in which the wave profile is a sine or cosine curve. Thus, if this wave profile at t equals 0 is phi at t equals 0 equals a cosine mx, then at time t, the displacement or disturbance is phi equals cosine of m times x minus ct. The maximum value of the disturbance, viz. A, is called the amplitude. So the crest or vis-a-vis the trough. The wave profile repeats itself at regular distances 2 pi over m. So here it's pi and m. In the differential equations, it's a often. This is known as the wavelength lambda for L. Lambda. Equation 3 could therefore be written phi equals a cosine of the quantity 2 pi over lambda times quantity x minus ct. Time taken for one complete wave to pass any point is called the period rho of the wave. Follows from the previous equation that 2 pi over lambda x minus ct must pass through a complete cycle of values as t is increased by rho. Thus, 2 pi c rho over lambda equals 2 pi. i.e. Rho equals lambda over c. So as you can tell, it very, very much employs the rotations is about the circle, because the circle doesn't have an end that's any different than its beginning. So instead of like implementing what they call the screw, which is like the Archimedean screw, it's like a circle from one perspective, but it has a continuous distance that it grows as it travels. That gets into the subfield of what's called screw theory, which is as with regards to how things are in the periodic and how they change, for example. So for scattering and tunneling theory, you can think of it as like an inchworm or something like that is how it goes along. The frequency, n, of the wave is the number of waves passing a fixed observer in unit time. Clearly, n equals 1 over rho, and so that c equals n lambda. And this gets into the great thing about frequency and wavelength of the periodic, that they're so inversely related and are a product of each other. And then as with regards to when those are separable, it's possible to define different various things about them. Great things. So anyways, frequency of wavelength of waves are probably the most fundamental concept that everybody would learn as an introduction to the formulaic approach to the symbolic approach to the theory of waves. The word for wave in French is onde, O-N-D-E, onde. And so the onde is kind of like the und, a watery thing, is the onde. It's like a droplet. Much of the theory can be found in developments in English and French in the scientific and technical literature as under waves or ondes. And then it starts getting defined. It talks about the phase. So phase is an important thing. Just like I don't know much about what a moment is, except it's with regards to it's any moment, any time and place kind of a thing. That phase is a thing. Sometimes it's useful to introduce the wave number k, which is the number of waves in unit distance. So we kind of have like the frequency versus the wave number, that they're just kind of per this or per that, each other reciprocally. If we compare two similar waves, phi 1 equals a cosine 2 pi of kx minus nt. So now it's in this parametric form according to the wave number. And phi 2 equals a cosine of this quantity 2 pi of kx minus nt plus epsilon, the difference. We see that phi 2 is the same as phi 1, except that it is displaced a distance epsilon over 2 pi k, i.e. epsilon lambda over 2 pi. Epsilon is called the phase. So we might call this phase displacement, vis-a-vis what is the phase of it, of phi 2 relative to phi 1. If epsilon equals 2 pi, 4 pi, dot, 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 then the displacement is exactly 1, 2, dot, dot, dot wavelengths for these harmonic waves with period 2 pi. And we say that the waves are in phase. If epsilon equals pi, 3 pi, dot, 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 then the two waves are exactly out of phase. So, even if a wave is not a harmonic wave, but the wave profile consists of a regularly repeating pattern, definitions of wavelength, period, frequency, and wave number still apply, and equations 5, 6, 7, and 10 are still valid. And then he starts talking about the plane wave, or the wave in 3 dimensions, kind of like we talked about the screw theory or something like that. That we get in different, however things radiate or oscillate, or however things like make their travels, the course of passage, the event. These are the parallel travel or transport. These are things. So briefly, that's just starting to talk about moments of waves, and it's kind of what I plan to do, is look at these books that I've gathered a little bit more thoroughly to go from some of these basic concepts of, a formulaic approach to how to talk about moments in motion. And from my perspective, geometry is motion, that it forms one complementary whole and a monist sort of approach to all that. And then with regards to that being a theory, and that one of its lemmas is that geometry is motion. This is Heidegger reading Parmenides. And so, like I said before, and I kind of belittled Heidegger for that. Well, what was his greatest achievement? Well, he copied all the ancient Greeks and translated them to German, and then kind of associated them with his concepts of continuous motion or time. It's like, well, how's philosophy going? It's like, well, we added time. All right, so now we have a concept of time. It's like before there was only being and nothing, and now you can also work with time. It's like, all right, it's continuous quantity. Anything I want to assign to it, it must so reflect that this is what it is. It so must be, es muss sein, that's what it is. So anyways, otherwise, he talks about Parmenides here, and Parmenides helps to establish a lot going on in the didactic poem. And so from the sleeve here, Parmenides, a lecture course delivered by Martin Heidegger at the University of Freiburg, presents a highly original interpretation of ancient Greek philosophy. A major contribution to Heidegger's provocative dialogue with the pre-Socratics, the book challenges some of the most firmly established traditional notions about Greek thinking and about the Greek world. So the Eleatics with Zeno include Parmenides and Heraclitus. And so from Heraclitus, we get dual monism or monist dualism in the dialectic at all. So in Zeno, we've got and here's time. And then so Parmenides, it was found by Heidegger to be the quite greatest thing of his Aristotelian comprehension of it vis-a-vis the Platonists. And Platonism is just a theory of that there already is a theory and it's true. So, work it up, that kind of stuff. Oblivion. The pole of the presence of things. The Greek's final word concerning the hidden counter-essence of aletheia. This sort of text introduces words in the Greek language, and it's important to know at least the letters of the Greek alphabet when reading any of these mathematical science works. For even trying to read out word by word, letter by letter, these words, but also because when the Latin alphabet, the Phoenician alphabet, the alphabet, runs out of characters and symbols, or to the side, then we'll use usually Greek letters, or script, or various typefaces, or as with regards to what these quantities are in the notation, what they're supposed to be. Superscript, subscript, building out the icon, the glyph. These are those kinds of things. So I'm not reading Parmenides now, but it's something that is good. There's lots in it, and in fact, there's so much in it you can find kind of what you want in it, but it's good. Technology understood as modern, i.e. as the technology of power machines, is itself already a consequence and not the foundation of a transformation of the relation of being to man. Modern mechanical technology is the metaphysical instrumentation of such a transformation, referring back to a hidden essence of technology that encompasses what the Greeks already called techno. Perhaps the transformed relation of being to man appearing in technology is of such a kind that being has withdrawn itself from man, and modern man has been plunged into an eminent oblivion of being. So the zeitgeist and angst of, obsolescence technologically is around, just as it is for, structures around. And so we have all philosophy who says, like, we already have one. It's the surrounds. So on Parmenides, it's we get to that he basically helps establish mostly that the theory of Parmenides is like, it's not that we know, it's that we can uncover things that already are there. We don't invent things. They're not an outspring of our mind vis-a-vis like, the usual notion of reproduction and that kind of stuff, which is like, well, it came from somewhere, that the idea then that otherwise we have the disclosure of stuff instead. So it's kind of an approach to the scientific method in the same one we have today. So now trying to figure out how to get this figured out, because I plan to look at this for a while, the moments in motion, and how to get it understood what I can of its relation to things fundamentally, and then elementarily, and then today as logically and symbolically. So didactically then for the elements as related to the canon, as related to the curriculum. Then with regards to the higher level edifices in effect today and what's going on in the science of the things and what all are the developments in that help so arise to attain to the understanding of things where a single pebble in a still pond could result all the intricacy of utter detail as to when it attenuates to the floor. It's like when you listen in the shell, is it still the sound of the ocean? Yes, it is. So this here is a book called Nonlinear Electromechanical Effects and Applications. And so it was read pretty thoroughly here before, and so it gets a lot into detail of, and it employs waves everywhere for things vis-a-vis forces and connections, or forces and couplings of stress and strains vis-a-vis crystallographic lattices and the deformation and pre-deformation of the configuration space and the mapping of the configuration space A to configuration space B. That's the entire kind of thing. That's the entire thing. This is a book called Radar and Sonar, and so in remote sensing, and this notion of being able to produce a wave and have it reflect from another object and return, and to evaluate its contents and to gain a new sense of it in this terms, is what radar and sonar is all about. Now it's to be sure, it's that there these methods are not like our usual intromissive vision, or the hearing of our ears, which is a tiny little set of dumbbells of connected together in the ears, which vibrate and resonate at particular frequencies and allow that to be converted to a sense of input data, the signal. Radar and sonar send tremendously loud or violent thing in the space otherwise that bounces back off that. It's extromissive in a very usual sense, and it interacts with this environment by interfering with it. So in terms of the passive and active, this is more as of an active system built as of a theory of waves, which is kind of why I want to study it, because it's and bring it in, because it's about waves and what results as of the observation that isn't at all, though, non-interfering with its surrounds, and so it's a different sort of thing. Is that kind of thing. Then here's this other book about it. It's called Waves and Layered Media. It's from the Russians. So after World War II, then it's kind of like there had been three major centers, and there became three major centers of technology and science. The United States and Russia, after Germany got split up. And so what was the continental kind of got split up, and then there was still, of course, France and England and that. And Italy and that science and technology of the time. And these days there's a lot more primary science and technology and what in those days were considered developing parts of the world, like China and India, vis-a-vis Japan. Japan, before and after, were very great adherents to the idea of the adoption of technology and science for all such manners of things. That for a long time, the United States and the Soviet Union were the centers of science. And now they had this whole ideological divide called the Cold War. This was after the close of World War II and what was considered fascist communism. Behind the Berlin Wall, which kind of walled itself off from the world, and then what was called, imperial capitalism, the free world or whatever it was called outside the wall, and they had their various epithets for each other and the reasons why they this or the other, right or wrong. I kind of course, I want the one where it's equal for me and everybody else, because that way I don't have to worry about trading and losing. Is the kind of thing that, though that so science and the relations of a usual kind of academic development together were not together. But anyways, this book is from the Russians and it's from 1980. So even before like the wall fell and all that kind of stuff, they were getting back together. There is scientific dialogue and discourse above such petty differences as the world's systems of government in the world and all that kind of stuff. And they are so science is so important to humanity that even such what you might call political or social divides, how that it ended up working out better for everybody. They got back together. So this is from a fellow named Braikovsky, and he says they designed. This is from the research of the Soviets and their sonar, and the waves. So it's all about waves, though. It's waves and layered media, and so it's a textbook and a treatise on waves, and from the time and the place for the whole wide world. Then this was kind of like something that would be approximately a reference work on what are the things known and how they're categorized as about waves as they're generally collected. So I figured to get to that a little bit more later. There's a little book here from R. Buckminster Fuller, and he was kind of a cyberneticist. So after World War II. Then there was operations research. It was like, well, we're going to use the great computer of all our operations research to kind of just plan everything out, and we're going to, get things organized. And then there was cybernetics. And so what cybernetics is systems engineering. And then systems engineering and the relation of man and machine. So cybernetics is this whole kind of concept of the man-machine interface and all this kind of stuff. Is how it rises and comes out and go around. So our Buckminster Fuller was a kind of a cybernetic and psychedelic thinker, and he invented a lot of great ideas. Like the Buckminster Fullerene is named after him. He said, I built this dome, and it's the cheapest way to get enough construction material to build the largest volume of building. It's kind of like the isoparametric theorem we talked about, But he talks about, at least when he starts off, he's got an overall theory, and it's kind of like, and it helps explain kind of one of these things. My continuing philosophy is predicated first on the assumption that in dynamical counterbalance of the expanding universe of entropically increasing random disorderliness, there must be a universal pattern of omnicontracting, convergent, progressive orderliness, and that man is anti-entropic reordering function of universe, and secondly, upon the assumption that man is born with an extraordinary inventory of faculties within an extraordinary inventory of universal phenomena. So that just kind of helps to explain that when our whole other theory is entropy and thermosecond law, and it comes down, and it's least action. At the same time, we're all organized people, and we're all thinking people, each with their own thoughts, in the wider world. Well, warm regards. Have a great day. It's a great day. Merry Christmas.